So here in 2.8, the derivative as a function. You can see here, this is the equation we worked with previously to find the derivative. Here they just simply replaced a with x instead. It's the same thing. In this section, mainly they're going to talk about sketching. If you're given a graph, how would you sketch the derivative? So the easiest thing to do first is to find the zeros. So think this is negative, this is positive, zero is about here, here, around here. That's my guess for zeros. This is negative slope, positive slope. Remember, derivative is mainly just tangent line and thinking about where the slope is. So negative slope, zero slope, positive slope, zero slope, negative slope, zero slope, positive slope. If you'd like, you could think about it as like you have a little car. Let's see if I could draw a little car. All right, and you have your car. If you were to drive along here, will you be going up or down? So down will be negative slope, and here you'll be flat. So when it's flat here, it's zero, and then up for positive slope, zero, negative slope, zero, positive slope. So at all the places that are zeros, let's look at those again. Here, about here, about here, all the slopes are zero. That, if we're drawing the graph of just the slopes, then it'll be zero, zero, and zero. And here we know that it's negative, positive slope, positive slope. So it will be something negative here, not exact, but something like that will be your derivative because we know from here to here, if we draw the line here, cutting off that zero, this is negative. So remember, on top is positive, on the bottom is negative. So we're drawing all the slopes. This is the negative slope here. We'll make this graph negative. This is positive all the way until here. Everything is positive because positive slope. Negative slope all the way until here. And everything else is here is positive. Let's take a look at the actual graph that the book gives us. So like I showed you earlier, drawing the zeros first is usually helpful. They actually approximated the slope here. So they drew a point, they drew a line, a tangent line, approximate tangent line, and found the slope. And so up, down, up. So you can see on this page there are different other notations for the derivative. They all mean the same thing. We're used to f prime of x, and then y prime is also derivative, dy over dx, and all of these are derivative. The one that you should make note of is d over dx. D over dx stands for take the derivative. A function f is differentiable at a if the derivative of a exists. It is differentiable on an open interval from a to b, or a to infinity, negative infinity to a, or negative infinity to infinity, if it is differentiable at every number in the interval. So the first part means that you can take the derivative if the derivative at a exists. So they're just mainly saying that differentiable means that the derivative exists. That's it. So if you had a question, I'll ask, where is the function differentiable? And you'll just have to look for where can the derivative exist. Here is an example of absolute value that we've seen previously in the other section. If you take the derivative of it for just x is larger than 0, it'll be 1. But if you take it for x is less than 0, it'll be negative 1. So it's differentiable both at x larger than 0 and x less than 0. Larger than 0, less than 0. Now the only thing is we need to look at the point 0. For x equal to 0, we have to investigate. You have to compute the left side and the right side separately because it doesn't exist at that point. You can't just put in the zeros. So here it will be 1, left side will be negative 1. And since these limits are different, f, the derivative at 0, does not exist. So f is not differentiable at 0, and it is differentiable everywhere else besides 0. So this goes back to the definition of a limit, and you need to check both the left and the right. If f is differentiable at a, then f is continuous at a. Okay, so if you could take the derivative there, it means that it has to be continuous. That makes sense. So in what ways can a function not be differentiable? So here are the three cases where the function is not differentiable. If there's a corner, if it is not continuous, or if there is a vertical tangent. It is differentiable here, but not here, because if you could take a look here, the slope changes. So when you're taking a derivative, I think what they're trying to show here is that if you zoom in and take a look at that exact point, what is happening. So higher derivatives. So not that you just do it once, but you could do it multiple times. The second derivative, we talked about it earlier, it could be meaning the acceleration a lot of times. So if the derivative is rate of change, what is the change of the rate of change? This means take the derivative of the derivative. Or you could use the double prime to represent the second derivative. And if you see 3, it's the third. Yes, familiar with acceleration. 3 marks, 3 primes, third derivative. The nth derivative, sometimes we use that. If you don't know how many, you take it n times. So the third derivative is also called the jerk, because a jerk means sudden change in acceleration. That's it for 2.8.